All the engineering we do is within the top few hundred meters within the ground, which is the crust. The three major elements of the crust are oxygen, silicon and aluminium, which are present as oxides. There are also smaller quantities of iron, calcium, sodium, potassium, and magnesium. Depending on how they are formed, rocks can be grouped under igneous, sedimentary or metamorphic rocks. Igneous rocks are formed by solidifying molten lava or magma. Sedimentary rocks are formed by deposition of sediments over years. Metamorphic rocks are formed by subjecting pre-existing rocks to pressure and/or temperature. While 65% of the Earth's crust is igneous rocks, 75% of rocks on the Earth's surface are sedimentary rocks. Soils are formed by weathering of rocks. If the weathered sediments remain at the same location as the parent rock, they are residual soils. If they are transported to elsewhere by wind, ice, gravity or water, they are called transported soils. All clay minerals are made of two distinct structural blocks, four-sided tetrahedrons or eight-sided octahedrons. A tetrahedron has an oxygen ion at the four corners and silicon at the center. Octahedron has an OH ion at the six corners and an aluminum ion at the center. Hundreds of tetrahedrons or octahedrons join at the base, forming a tetrahedral or octahedral sheet. Stacking the tetrahedral and octahedral sheets in different ways, different clay minerals are formed. Three common clay minerals are kaolinite, illite, and montmorillonite. Montmorillonite has weak van der Waals forces holding the sheets together and can be easily separated by water getting between them, making the clay swell. Isomorphous substitution happens in clay minerals when high-valence cations are replaced by low-valence cations. That gives the clay particle a net negative charge. Cation exchange capacity is the capacity or ability of the negatively charged clay particle to attract cations. When the particle has larger surface area, It has larger area to attract cations. When the grains become finer, the specific surface increases. Montmorillonite has about 800 square meters for 1 gram. Adsorbed water is a very thin layer of water firmly held to the clay particle that cannot be removed by heating to 100 degrees centigrade. The purpose of this exercise is to show that when the grain size decreases, the specific surface increases. The clay minerals plot in specific locations in Casagrande's PI versus LL chart. Montmorillonite plots just below the U line and illite plots just above the A line. Kaolinite plot just below the A line. Crudely put, activity quantifies the clayiness of the clay. It is the ratio of the plasticity index to the percentage of grains finer than 2 microns. High values of activity, say larger than 1, suggest potential swell-shrink problems. Unlike silts or sands, clay particles are like flakes or sometimes needles or tubes. A packet of clay particles can be oriented randomly or they can be oriented in a specific direction. The first gives a flocculated fabric and the second gives a dispersed fabric. Very often it is in between the two. Here is a scanning electron micrograph showing a kaolinite clay fabric. The scale shown is 5 microns. You can see hundreds of flakes stacked together and oriented in different directions. Although clays and silts are both fine-grained soils, they behave very differently. Clays are electrically charged, cohesive, plastic, and are sticky when wet. Silts are like very fine sands, non-cohesive, non-plastic, inert and gritty when wet. When dry, clay lumps are difficult to crush and silt lumps are easy to crush.